folks, we're going to be talking about inverse trig functions today, so inverse sine, inverse cosine, inverse tangent. We're going to refer back to quite a bit the unit circle and drawing pictures. Triangles are one of the 4 points for the unit circle with this, but we're starting out thinking about some questions on the graphs that we focused on last chapter. So what I'm going to have you do, if you would, is read through this and answer questions 1 through 4, where I talk about a little bit of vocab that goes with that question 4 when you come back. So pause the video and try those for me. Okay. These ones you are fine to put in your calculator as long as your mode is in radians. Otherwise, you'd have to convert that to an angle of degrees in order for it to come out nice. But what I want you to do is think about this also in terms of, like we were talking about, the unit circle. So if we think 7 pi over 6, remember this pi over 6 says 180 divided by 6, which is 30 degrees. So it's a 30-degree triangle. And if pi is here, 7, 6 would be a little past that. So I'd have a 30-degree triangle right here. And then if I think about the sides of that special triangle, we've got 1/2, square root of 3 over 2, and 1. Signs are important as we think about the unit circle based on what quadrant they land in. So going to the left and going down, both negative. I want the sine value, which corresponds to the y value of that triangle. So negative 1/2. And because all of these are the sine with some sort of 6, they're all going to be either positive 1/2 or negative 1/2. And hopefully when you type them in, you got all of them to be negative. And we're going to talk about why. So placement on the unit circle, this negative means clockwise. So add that on there just as a reminder. And that would put us in quadrant 4. Sine is negative going down in quadrant 4. 11 pi over 6 is 1 and 5/6. So 1 pi, 5/6 pi. That's again in quadrant 4, another version of the same thing. 19/6 pi is 3 and 1/6 pi. So here's 1 pi, 2 pi, 3 pi, 1/6 more. Land you in quadrant 3, another version of that 7 pi over 6. So all of these values have the same result. And when we think about plotting these, they're all along this negative 1/2 line going across. And so these were the 4 that corresponded to those. We have another one at negative 5 pi over 6. And it keeps going forever. So when we talk about how many solutions, there are infinitely many when we're talking about an equation. So I do want to emphasize that this is an equation from this equal sign. And with any periodic function, we're going to have infinitely many solutions to an equation if there are solutions at all. Okay, but that's not quite the same thing as the next question is asking. If you type this in your calculator using the inverse sign versus using the regular, notice it's giving me that y value, and it wants the angle back. Okay, so remember, an inverse is going to solve for the angle. And your calculator, if it's in degree mode, will give you negative 30. And if it's in radian mode, it's going to give you the decimal version of this negative pi over 6. So it's not giving you all of them, it's just giving you one of these values. So this is an expression. And the biggest difference between an expression and an equation is an equation is going to have infinitely many if we're not restricted. An expression will only have one answer. And that one answer comes from some requirements that we're going to set up. Okay, the requirements come from this definition on the next one. It asked was sine 1:1. You haven't seen that a whole lot, that 1:1, but we've actually used it quite a bit. In fact, we've used it this year. The test to decide if a function is 1:1 is the horizontal line test. Basically, it's saying on this graph, do I have an individual y value going to one x value, or does it go to multiple? So I'm focusing on this y value of negative 1/2. And for us, that is going to multiple x values, which means it would not be 1:1. And essentially, that means it's failing the HLT. That's important to us because the HLT is a test that we have used this semester to talk about inverses and whether inverses are going to be functions. Remember, on a normal graph, if the graph passes the VLT, it's a function. That's why this graph is a function. But if we want to know if the inverse will be a function, we do the HLT. So by this failing the HLT, we would say that the inverse is not a function. And in Chapter 1, when we had functions that we were working with that didn't pass the HLT, we didn't bother finding their inverse because their inverse was not going to be a function because it's not very useful to us. When the inverse is not a function, it's not something we can input in our calculator because there are multiple outputs that should come out and our calculator can't do multiple outputs. But we did use our calculator on this, and that's because we're able to restrict the graph to make it work. Here's what I can refer back to that we've done actually this year. We looked at a square root function, and when we found the inverse of that, it ended up being a quadratic, but it wasn't the whole quadratic. We restricted it. We only looked at part of it that matched the original function. This is going to be similar, but going the other direction. What we're going to do is restrict the original graph so that when we do that reflection, when we switch the x and y around, we end up having only that one output, or we end up having a function as a result. Okay, so here's what I'm going to ask you to do. We are going to cut down the domain of this graph, and we're going to do so that we're picking the biggest interval with no repeated outputs, and again, that just means no repeated y values. So I want you to think about picking a chunk of this graph where you wouldn't see the same y value happen twice. And we want the largest interval possible. Okay, so pause the video and see if you can come up with what that interval might be. Okay, there actually is one other requirement, so I'm going to have you add something here. When we talk about interval, first of all, that means continuous. We don't want to pick multiple chunks. We want one chunk from here to here. And then the one extra requirement goes back to how you use the inverse. Up until this point, you use the inverse to solve for an angle. Well, when we talked about angles before this class, a negative angle wasn't something that was possible because a lot of times we used it to solve for an angle in a right triangle. And with that, we want them to be positive values. So when we're thinking about the values in a triangle that are possible, with a right triangle, these are both acute, which means we would want the angles 0 to 90 degrees to actually show up. For us, that means quadrant 1, or we want to make sure on this x-axis we're including 0 to pi over 2. Okay, so we have to include from 0 to pi over 2. That's a requirement. Okay, and if I want all of the y values but no repeating, I can't go past that because that repeats those y values. I have to go backwards. So what I want you to do on your graph is mark these endpoints for me. And I want you to darken or highlight along that curve because that's the section of this sine function that we are choosing to go forward with to find the inverse. Okay, so the interval is from negative pi over 2 to positive pi over 2 included. Okay, and I want to indicate that this is our restricted domain. When we restrict the domain, our range will not change. We're still going from -1 to 1 because the purpose is to choose the section of this graph that hits all of the y values but doesn't repeat them. Okay? So thinking about inverses and what we know, our x values along this is our angles, and our results, the y values, are talking about the ratios. So I'm going to have you add to this for the original parent function. X is talking about angles, y is talking about ratios. So in this case, it's specifically the sine ratio, opposite over hypotenuse. Biggest that can be is 1, smallest it can be is -1. When we go to the inverse, and you don't have this, but I just wanted to show you, okay, when we go the inverse, all that happens is those values switch around. You'll notice this x value goes to 1. That's talking about our ratios. And the y values go to the angles. because that's the output of the inverse. When we use an inverse, it's to get an angle. That's our result. So if I wanted to find the domain and range of the inverse, all I would have to do is switch the domain and range from the original. So the restricted domain from what we just talked about was negative pi over 2 to pi over 2. That is the range for this. And we can see that from this visual. Again, you don't have this, you don't need it. We're not going to, I'm not going to have you need to know what the graph looks like or ever have to sketch it. What you need to know is what the inputs and outputs are. Okay? We need to understand that when we're talking about the inverse, the thing that goes inside of it is the ratio, and the thing that comes out of it is the angle. Okay? And then just as a reminder, that reflection I've been talking about when we talk about the inverse is always over the line y equals x. There's my original and reflected over based on just switching around that x and the y value. Okay, so now what I'm going to have you do is think about this same process for cosine. So pause the video and try number 6 and number 7 for me. Okay. This one, hopefully you got a no. We cannot use the same one because if I went negative pi over 2 to pi over 2, I'm all positive, okay, and I'm hitting some repeated values. Instead, we want to go from 0 to pi. So my restricted domain is from 0 to pi included. I'm going to have you add the range here as well, just to emphasize that when we restrict the x values, we do not change the range. It is still negative 1 to 1, as the original parent function was. Okay, but you're supposed to evaluate this. Okay, remember, for an expression, you should only get one answer. Okay, and if you put it in your calculator, that answer in degrees is 135. But that is the same thing as 3 pi over 4. And hopefully you can see that on your graph. Let's chat for a minute. Okay, this corresponds to the y value here. And negative square root of 2 over 2 is close to negative 0.7. So here's my negative 1. 0.7 would be right about here. And we're thinking about the x value that goes with that. We can see there's half, there would be 3/4. Okay. What I want to tie this together with, because this is what we're going to do on the back side, is how we can solve this using our knowledge not just of this graph, but of the unit circle, which is sometimes more obvious. Okay, so if we're thinking from 0 to pi, that would mean we go 0 to pi, only use this first top half, first 2 quadrants. And then we're thinking about where cosine, or the x value, is negative. And so that would have to be this left section. And the triangle that has a square root of 2 over 2 on it is a 45-degree triangle. We know a 45-degree triangle has to be some fraction of 4. And because I'm here backwards, I haven't made it quite to 4/4. I end up with this 3/4 pi. That's a process we're going to kind of work through when we get to that backside. Okay, just a reminder of inputs and outputs before we move on to the graph. Okay, this is my angle. This would be my cosine ratio, which for SOHCAHTOA is adjacent over hypotenuse. When we think about the inverse, those two things switch. So this graph, my x would be my ratio. You'll notice from left to right, it goes negative 1 to positive 1. And my angles are my output, and we're only going to see values 0 to pi on those ones. Okay. With that in mind, domain would be negative 1 to 1, flipped from what we just talked about. And then the range would be from 0 to pi on our inverse. Last problem is tangent. Same process for this. I want you to pause the video and give me the restricted domain for this. Okay. This one was similar to sine, not quite the same. Okay, we still want to include that quadrant once. This has to be a part of it, but we have to go backwards. So how it's similar is we're still seeing negative pi over 2 to pi over 2. What's different is this graph has asymptotes, which means we are not including those two endpoints. Tangent is undefined at those values. Another thing that's different about tangent is the range. Okay, the range for this is not from -1 to 1, it is from -infinity to infinity. And that goes back to what you think about tangent. Remember, the ratio for tangent is opposite over adjacent. This ratio does not include the hypotenuse, which means there's no rule to say that the opposite has to be smaller than the adjacent, which means I could have a much larger value on top than on bottom and end up being larger than 1. Again, angles here, and when I talk about the inverse, that's reversed. Because I can have a ratio greater than 1, the domain is all real numbers here on the inverse, and the outputs only are those -π/2 to π/2. You can't get those values itself again because we can't type in undefined. Okay, we can't have that as a ratio. Okay, so now we're going to solve some problems similar to what we did on that one example. To do this, we have to realize that these are expressions, which means there's only one answer possible. Okay, and then we're going to identify the domain so we know where that one answer shows up. Okay, so starting on this one, our domain that cosine gives us, we decided was from 0 to pi. So to draw this picture, we're going to include the option 0 to pi, which is the top half, and we're going to get rid of all the other ones. Then we're going to think about this ratio. When we think about that thing inside, it could be one of our 4 original points from the unit circle, or it could be a triangle. In the case of a fraction, we're usually looking at a triangle, and this is positive, so cosine is positive. In fact, everything is positive in quadrant 1. So then we just have to think about what kind of triangle, a 30, 60, 90, or a 45, 45, has that ratio on it. So as a reminder, if you need it, the 45, 45 is the square root of 2 over 2 for both sides with the hypotenuse 1. And the 30, 60, 90 has the ratios 1/2 and square root of 3 over 2 with the hypotenuse 1. So for us, we're looking at this triangle. And because both of the sides are square root of 2, we don't really need to label them because the goal here is to find the angle. That's our output. But when we talk cosine referring to the unit circle, remember that's the x value. So we're saying that this side is square root of 2 over 2, which makes our angle 45 degrees. So the answer is 45 degrees, but we want it in radians from 0 to pi. So that is pi over 4. Another thing that might be helpful, remember 45 degrees goes with something over 4. 30 degrees goes with something over 6. And 60 degrees goes with something over 3. Next one is same concept. We're starting with 0 to pi. But this time, cosine is negative, which means we have to be in quadrant 2. Same process, we're thinking the x value. So along this bottom side is -1/2. Now this we know is either a 30 or a 60 degree angle in the corner from that ratio. And sometimes it's helpful to put the other side on there so we can see it more clearly. But the goal is always the angle, so don't lose focus of that. Across from that would be the 60, since it's the larger ratio with the larger angle. And remember, the goal is the angle, but it's the angle all the way over there. It's in second quadrant. So second quadrant starts after pi over 2, between that and pi. So we know if we see 60 degrees, it has to be something over 3. So I'm going to call this 3/3. And then this point, I haven't made it to 3/3 yet, so my answer is 2/3 pi. Okay. The next one has a notation that's slightly different. It says arc sine. When you see this arc sine, it literally means the arc, or the angle, whose sine is -1. It's just an older version of saying inverse sine. So first thing we're starting with, we've got a new interval to focus on. Sine uses from -π/2 to pi/2. So we are looking at from negative, or clockwise, pi/2 to clockwise, or counterclockwise, pi/2, which means quadrant 1 or quadrant 4. add a little note, that's the clockwise version. So we have to decide where -1 is possible. So first of all, when we're looking at sine, remember that's the y value, and we want to know where the y value is -1. Okay? Well, thinking about that and your triangles, we're never seeing a 1 on the y side. We're seeing a 1 for the hypotenuse, but not along the side of the triangle, because this one is out one of the original ordered pairs. Don't forget that those 4 points from the original set are options, and this is my ordered pair 0, -1 that I'm looking for. But remember, the answer is the angle, not the ratio. I'm given the ratio. I want to know what angle gets me there. And any time I'm in quadrant 4, the answer has to be clockwise or negative, and it's right at that -pi/2 itself. Okay. I'm going to have you pause the video and try out that next one for me. Okay, hopefully you got same restriction as last time. We're going to actually be in quadrant 4, which means I know my answer is negative. And then the angle I'm looking for here is based on this y value being negative square root of 3 over 2, which makes it a 60. So -pi/3 is my final answer. Okay. Tangent ones are a little bit weird, but we're going to start with the same process. -pi/2 to pi/2 gets me the correct placement. So I'm only from here to here. And it's still a triangle because we've got this fraction going on. But then we have to figure out which part is across based on what we know about where this number comes from. So I'm going to backtrack a bit. The square root of 2 over 2 comes from a rationalized version of 1 over the square root of 2. Similarly, the square root of 3 over 3 comes from the rationalized version of 1 over the square root of 3. So I want you to write that to the side for me. That's something you have to be able to recognize, because you're not seeing the square root of 3 over 3 on either of these sides. It comes from taking sine over cosine, so either 1/2 over the square root of 3 over 2 or the square root of 3 over 2 over 1/2. We have to decide which part goes where. So to do this, the easiest way to think about it is going back to SOHCAHTOA. Tangent is opposite over adjacent. So we can let the opposite side be this 1, and this adjacent side be the square root of 3. So that's a -1 and a square root of 3, based on I know going right and down. And then I can see the two sides as they should be. Based on that, we have to have a 30 degrees in the corner. And remember, quadrant 4 is always clockwise. So we're going to have -pi/6 for the final answer. Okay. Next one, inverse tangent of 1. Still in these two quadrants, possible. Okay. 1, a lot of times when we see 0 or 1, we think it might be one of the original 4 points. But I want to remind you, when we think about tangent, tangent is undefined here and here, pi/2 and -pi/2. And tangent is 0 at 0. Okay, so it's never 1 at those original points. For tangent, though, when we see this 1, it really is a triangle. And specifically, if you go back up here, we're thinking about where our sine over cosine is equal to 1. That only happens on an isosceles triangle. Since it's positive, we're in quadrant 1, and we know it has to be that 45. So final answer, pi/4. In the instructions, it said if you can't find an exact value around 100ths, that's going to be these times where you see these really ugly decimals. Okay, these are just calculator problems. Okay, the biggest thing is you want to make sure that your mode is correct here. So this is my ratio, thinking about this is -0.8. Okay, that would happen somewhere down here. So I'm going to have a negative answer for my clockwise. And all of my answers so far I've been putting in radians, so that's the mode I should be in. Similar here, this is inverse cosine. 0.99999 is really close to 1, so this is going to be close to a cosine value of 1. Cosine is 1 here, so it would be somewhere right about here. Again, small angle, but this time it's going to be positive. Type those in, Make sure your mode is in radians, and then you're going to approximate to 2 decimal places for each of those. Okay. Now, all we've been talking about today are inverses, but it comes from the same type of math that we know normally. If I have 2x plus 1 equals 5, I can solve this by saying minus 1 and then divide by 2. But I know that because of inverse operations. These cancel out because plus and minus are inverse operations, and that's what's supposed to happen. Here, this is 2 times x, so to get rid of it, I divide, because multiplication and division are inverse operations that cancel each other out. So when we're talking about sine and cosine, an inverse sine and regular sine should cancel each other out with one exception. We just learned that the inverse sine is only a function if we restrict to a certain output. So when we think about this, we want to think about the angles that are possible. So with sine, the only angles that are going to come out of it on the restricted domain are from negative pi over 2 to pi over 2. So these will cancel out as long as this number that we see inside is within those values. So if we think about 5 pi over 6, we land in quadrant 2, and 5 pi over 6 is not from negative pi over 2 to pi over 2. Okay, so this one is false. And our reasoning is 5 pi over 6 is outside of our restricted values. Okay, so we're going to be asked on the next part to actually find what this is, so we'll practice now. When we think about this expression right here, it's sine of 5 pi over 6. So let's go back to this triangle. I want you to sketch it if you haven't. If we're thinking about 5 pi over 6, I know that this angle right here in the corner is 30, and I know the sine value of that would be 1/2. So that doesn't work. However, I can find the angle if I looked at a sine of 1/2 in a quadrant that was acceptable. So we're looking for where a triangle I could place, first quadrant or fourth quadrant, where the sine value would be the same. And so because of symmetry, that would have to be directly across to get that 1/2 to match. So then my actual answer is 30 degrees in the first quadrant, which means it should be pi over 6 itself. Okay. On this one, we're going to think about the same thing. These cancel out if the outputs that are for this outside function is actually, or this number is falling within those outputs. So cosine, if we think about the range or the outputs, is -1 to 1. We just have to decide, are those values, is that value between -1 and 1? And it is. So this one's true. And as long as this number is a ratio that's possible for cosine, then you're all good. That's something that we see on a cosine triangle. Okay, it's something we see on that 45-45 right triangle. Okay, but as long as it's less than 1, it's an adjacent over hypotenuse that's possible, these ones will cancel out. So most of the times they will. But when the inverse is on the outside, that's where you have to be careful. That's what we're going to practice on these next 3, is the inverse is on the outside for all of them. So first thing I want you to do is identify the restricted domain of the original, which tells us the output of the inverse. So the output for this is negative pi over 2 to pi over 2, which means this answer is okay as long as it falls within that range. So 60 degrees is in quadrant 1. Quadrant 1 is always okay. So 60 degrees is fine. We'll just write it in radians like we have been doing. Okay, same thing for cosine. The output of this thing is 0 to pi. And so that means as long as this is between 0 and pi, we're good. Okay, this is obviously too big, so let's draw a picture of where it would land. Okay, all the way around is 360. 390 would be just 30 degrees more. And 390 is not okay, but we do land in quadrant 1. And quadrant 1 is always okay for any inverse. So quadrant 1, we just have to change this from 390 to just 30 degrees, which we want to call pi over 6. Okay. I want you to pause the video and try that last one. It will be a little bit challenging. They do not cancel because this is supposed to be from negative pi over 2 to pi over 2. So this is too big. And in fact, this is in quadrant 3, and none of our inverses allow us to be in quadrant 3. But the angle here is going to be 60 for us. And we're thinking about the sine value. So we think about this y value. So we're just using symmetry to decide where can I place this triangle where it would have that same y value. And that's over here. Again, I don't need to know what that ratio is. If it's a nice triangle, you can find it, but it won't always be. This could have been 4/5 pi. And I wouldn't necessarily know immediately what that angle is or what that ratio is. Okay? I don't need to know that. I just need to be able to solve for the angle once I move it. So here, it's still 60 degrees, but if I'm in the 4th quadrant, remember you have to say clockwise. So negative 60 degrees, we call negative pi over 3. Okay. Those will take a little bit of practice of getting used to, okay, but please come in if you have any questions on your homework in regards to this. Last thing I'm going to do here is just a couple word problems with you that relates to inverses. Okay, this is similar to what you did on last time's assignment, just some practice being careful on looking at some particular extra steps. So here we've got a satellite. It says the altitude of the satellite is 705. They've given us a picture with the altitude here, so I'm going to go ahead and add that. Then it says C is in the center of the Earth. It's already labeled. H is on the horizon, already labeled. S is the satellite, already labeled. We want to focus on the angle HCS. So HCS puts us in this corner, and that's labeled as well. Okay, it says write a formula for theta. This just means I want theta equals, just as a heads up, in terms of R and A. So this means don't put numbers in yet. So let's go to work. On our triangle, our right angle is here. This would be from this angle, the adjacent side. And then I've got other stuff here on the hypotenuse, which means we're going to use cosine as our parent function. We always start with cosine theta equals the ratio. So our ratio is adjacent first, R. And then the hypotenuse, we want both of these together, so we'll have to add them. And then we solve for theta using the inverse. Okay, so there's our formula, step 1. Then it gives us the radius so that we can solve for the angle. So cosine inverse, our radius is 6,378. And then on the bottom, we want to take that 6,738 and we want to add it to the 705. You want to simplify before you put stuff in. Okay? Oh, I mixed those around there. So 6,378. Plus 705. 7083. And then we can actually type that whole thing in. If you don't simplify first, your calculator is going to give you the wrong answer, so watch out for that. And then this looks funny because remember I'm still in radians and it wants the angle to the nearest degree. So that means make sure you change your mode to degrees. Now in this case, it was pretty obvious that something was wrong. But you want to pay attention to your mode always based on either what you're given or what you're asked for. So about 26 degrees based on instructions. Okay. Next one, we've got a plane flying at an altitude of 32,000 feet. So got my plane here. And my altitude is 32,000 feet. And it says it descends at a constant angle theta to an airport runway X miles away. Okay, so here's my runway, and I'm going to hit that point to make my right triangle. And it says that airport is X miles away, so that goes there. And here's the weird part. If it's descending, we're thinking about the normal path is this plane is flying straight. But then they're going to start heading with that tip of their nose down. And so that's my angle of theta, which is equivalent to this angle in the triangle. When you see angle of descent, angle of inclination, angle of elevation. Make sure you always put theta on these right triangles with the horizontal piece, not with the vertical piece. If you don't, you're going to see some really weird answers. But based on that, we've got some problems here because this is in feet and this is in miles, and they tell us we want it in miles. So we've got to do some conversions here. If I have 32,000 feet, I want to divide it by 5,280 to get it to miles. So I've got 6.06 repeating, or 200 over 33 as fraction. Okay, the reason I went ahead and changed this to a fraction as well is because of some technicalities with math here. We know that this is going to be opposite and this is adjacent, so we're using tangent. And when I set this up here, you're not technically allowed to have a decimal inside of a fraction. It's not proper, which is why we'd want to use this fraction version instead. And wherever the bottom part of the fraction is, it goes with the bottom part of the fraction here. So when we solve for the angle, we use inverse tangent, and then we can write that as 200 over 33m. Okay? And then we want x equals 40. So here, sorry, this is x, not m. And once we plug that in, just like on the altitude problem for the satellite, we have to simplify that first. Take your 33 times your 40. Otherwise, it's going to not understand order of operations. Then we can do that inverse tangent of that ratio. So it's about, says nearest degree, about 9 degrees. Okay. Think about what you want when you're going on a plane this angle of descent to be. Okay, if we get too much over 10 degrees, that's probably a scary descent. Okay, because angles over long periods of time get pretty fast if we shorten this length up. Okay, so we need a relatively small angle for problems like these. Okay, the last one is pretty similar. Ladder against a building. Here's a building, here's a ladder. See our right triangle, and it's 18-foot ladder. And it says the building is 30 feet tall. We're assuming it's going all the way to the top because they didn't tell us otherwise. It says find the angle the ladder makes with the ground. Okay, so we've got opposite and hypotenuse. So that would be sine. Theta equals 30 over 18. So we just need to use the inverse sign to solve. This one, there's no worry about simplifying. You just want to make sure that number is reasonable when it comes out. Okay, think about an angle against the building. We don't want something too small or it'll fall down. We don't want something too steep, otherwise the ladder's literally smushed up against the wall. Okay, so this one, oops. Okay, I thought I had something wrong here in my calculator. That's not it. It's something wrong with the problem. Okay, check this out. Okay, this is a situation that's not possible. Okay, because if I have to get 30 feet up the wall, and I'm going to the top of it, because it didn't give me context otherwise, an 18-footer is not going to do it. Okay, the hypotenuse has to be greater than the opposite side. So this is one of those ones, if I had a problem like here, with the regular on the outside, okay, this is not a ratio, 30 over 18, that would be possible. Okay, so that's really a no solution problem. Okay, if you struggle at all on your homework, please come see me, especially as you draw those pictures either for those non-calculator problems or those word problems.